Today, we are going up against a true mathematical beast, a problem so ridiculously complex that for the longest time, everyone just agreed it was unsolvable. But what if there's a hidden key, a totally new way of thinking that claims to have cracked the code? Well, we're going to see exactly how it works. So just take a second and look at this thing. It's an 18th degree polynomial. It has 19 different terms, each one getting more and more complicated. For centuries, finding an exact, perfect answer to something like this, well, it was basically a mathematical nightmare. So really, where would you even start? All right, don't worry, we're not just going to throw you in the deep end. We're going to break this down piece by piece. First, we'll talk about why this equation was considered impossible. Then, we'll see why the old ways of solving it just weren't good enough. After that, we'll introduce the brand new theorem that changes everything, watch it do its magic, and finally, reveal the exact answer. Okay, first up, the unsolvable equation. You see, to really get why this new method is so brilliant, you first have to understand why this type of problem has been such a massive headache for mathematicians for so long. For hundreds of years, mathematicians had formulas for simple things like quadratic or cubic equations. But once you got to the 5th degree and higher, bam, they hit a solid brick wall. There's even a theorem that proved there is no general formula for them. So mathematicians had to settle for approximating, just getting close to the answer, but never ever finding the exact one. And that whole idea of just getting close brings us to the real problem with approximation. For decades, the best tools we had could only give you an estimate. It was always a trade-off. Do you want a practical answer or do you want a perfect answer? You couldn't have both. And this right here is the heart of the matter. On one side, you've got your traditional numerical methods. Think of them as a process of guessing and checking, over and over, getting a little closer each time. But every tiny calculation introduces rounding errors, so what you end up with is an approximation. It's like a blurry photo of a key. Ezeudi's theorem, though, is totally different. It uses a direct, step-by-step calculation to give you the exact symbolic answer. It's not a photo of the key, it's the actual master blueprint for the key itself. Which brings us to the hero of our story, Ezeudi's theorem. This is a fundamentally new approach that completely challenges the old idea of what's unsolvable. I mean, listen to this quote from the theorem's creator, Morad Sultan Ezeudi. This is incredibly bold. He's not just saying his method is a little better, he's saying it completely sidesteps the classical rules that told us for 200 years that this kind of exact solution shouldn't even be possible. So what is it really? Well, at its core, Ezeudi's theorem is a special kind of tool. It uses a recursive formula, meaning each step builds on the last, to calculate a whole new set of numbers that magically simplify the original equation. It lets us find the exact roots without ever having to guess or round anything off. Okay, and here it is, the engine behind the whole thing. Now, I know it looks like a mess of symbols, but don't worry, we are not going to try and solve this by hand. What's important here isn't the complex math, but the absolutely brilliant idea behind it. So think of this formula as having 3 key ingredients. First, you have these things called binomial coefficients, which act like weights to control how much influence each part has. Second, you have the recursive memory, which means every new calculation is smart because it builds on the one that came before it. And finally, it's all built on a foundation, the original numbers from our big, messy polynomial. And now for the really cool part. Let's actually put this method into action and watch as the calculation unfolds, turning that absolute monster of an equation into something we can actually solve. So we start the process. We plug in our first value, k equals 0, let the formula do its thing, and the first new coefficient it spits out is 0. Okay, simple enough. So we move on to the next step, k equals 1, and we get 0 again. We try for k equals 2. Still 0. In fact, step after step after step, all the way up to k equals 8, the formula just keeps giving us the same thing, 0. At this point, you might be thinking, is this thing broken? Is it even doing anything? But then, on the 9th step, everything changes. The pattern shatters. The formula finally spits out a number that isn't 0. It's this huge value, but it's real. This is our first breakthrough. This is the first important piece of the puzzle we've been looking for. We keep this process going for all 18 steps. And it turns out, after all that work, nearly all of the results are 0. We're left with just 2 non-zero values.
that s sub 8 we just found, and one more way at the end, s sub 17. That's it. These two numbers are everything. They hold the secret to simplifying the entire problem. And that brings us to the grand finale, the exact symbolic solution, all unlocked by those two little numbers we just found. Remember that chaotic 19-term mess we started with? After we plug in our two key coefficients, the whole thing just collapses into this. A beautiful, simple 3-term equation. All that insane complexity has been boiled away, leaving just the pure, essential core of the problem. It's an absolutely incredible transformation. And here is the final beautiful trick. This new equation might look complicated, but if you just pretend that x to the 9th is your variable, well, it's just a simple quadratic equation. We can now use the good old quadratic formula from high school to solve it directly and find the precise symbolic roots. No guesswork, no approximation. Done. And that is the ultimate prize, a symbolic root. It's not a long, messy decimal that's been rounded somewhere. It's the perfect, exact mathematical expression for the answer, square roots and all. It's the difference between having a blurry photo of a treasure map and actually holding the treasure right in your hands. So this leaves us with a pretty cool question to think about. We just watched a problem that was a total dead end for generations get completely taken apart by a new way of thinking. So if this unsolvable problem wasn't actually unsolvable at all, what other impossible challenges out there are just waiting for the right person to come along with a new perspective and crack them wide open?